Okay, welcome back. So, finding position from velocity. So you have that the instantaneous velocity is dx dt. So let me write it this way. I have dx dt is v is equal to v. So if I integrate both, if they're equal, I can just integrate both sides with respect to t. This is the symbol for integral. And I can integrate both sides from t initial to some t final. This one also from some t initial to some t final. Now the left side, notice, you take the derivative and then you integrate, you get back the same function, right? If I take the derivative of a function and then I integrate it back, I get back my function. And I get back just my function, x of t, evaluated between t initial and t final. You know this from the fundamental theorem of calculus, right? Part 2. And so, and then this side is just also the integral of the velocity dt. This one I cannot proceed any further until I know what the velocity is as a function of time. T initial to t final. We'll do an example of this. And so, how do you evaluate this? You evaluate it at the upper limit, so it becomes x at t final minus evaluated at the lower limit, x at t initial. And then here you have the integral of from t initial to t final of v dt. And x at t final is usually just called x final. And x at t initial is usually called x initial. Equals to integral from t initial to t final of v dt. Okay, so that's that. I'm going to look for an example here. We're given the, and by the way, when you do the integral of a function, it's like you're evaluating the area. The geometric interpretation will be the area under the curve. So let's do an example just to demonstrate that. So here's the example. The velocity of a particle is shown in the following graph. It's shown in the graph. Here is the graph. Here is the velocity. This is 10. The velocity, of course, is in meters per second. Meters per second. This is 2. This is 4. This is 6. 2, 4, 6 seconds. This is the time. It's in seconds. The velocity as a function of time. And we're given that also the initial position is x initial equal to 30 meters. The position of this thing, of this particle, is at 30 meters. By the way, we say a particle, an object, a person, a car, a point. Everything is usually we call a point or a particle. Okay? Everything is a point mass as far as we're concerned. So you got this object that's moving, and it's moving at 10 meters per second initially, and then it moves at 9 meters per second, 8 meters per second, 7 meters per second. So it's still moving. It's still moving. So you can imagine, here is the x-axis. It starts here at x equal to 30, right? Because the initial position is at 30. And at that, when it's here, the velocity is 10. So it's still proceeding forward, although the velocity is decreasing. It's like you're going in your car, but you take your foot off the gas. So the car slows down, but you still make progress forward until the car stops. So it keeps moving forward, the position keeps increasing till it gets somewhere here, and then it starts maybe make a U-turn and come back. Okay. So the first question is, at what time does the thing turn around and come back? Notice that as long as the velocity is positive, by the way, the convention is we have to choose an axis or a reference point or a coordinate system. Here is our coordinate system. Here is 0. If you move this way, that's positive. If you move this way, that's negative. So as long as the velocity is moving that way, or the object is moving in that direction, the velocity is positive. When the velocity becomes negative, it means the object has turned around and is coming back. It's like this chalk. If you throw it up, when it's going up, it's positive velocity. When it's coming down, that's negative velocity, if we consider up to be positive. So the turnaround point is at 2 seconds. That's when it turns around. So at 2 seconds, it turns around. So the question is, what's the position at 2 seconds? Find x at 2 seconds. So I'm going to solve this problem the first way geometrically, and the second way using calculus, using the integral, like this. Okay. So what's the position at 2 seconds? Well, we know that the position, we said the position is the integral of velocity, so it's the area here. So it's this area up to 2 seconds. What is this area here? How much is it? Well, it's a triangle, so it's half the base times the height. So it'll be the half the base, 1/2 the base. The base is 2, right? From here to here is 2, times the height, that's 10. Half of 2 is 1 times 10, so that's 10. That's 10 meters. So the position at 2 seconds, it started at 30, but then it moved further by 10 meters. So it's actually at, that's too far. So that's 40. So it moved an additional 10 meters. So that is, it's at 40. So x at 2 seconds is actually 40 meters. Okay, that's that. Now here is the next question. The next question is, at what time is the position 0? Right? So it moved forward. At t equal to 2 seconds, it turns around, and then it comes back. It comes back. At what time does it come back to 0? Okay. Well, notice now, it has turned around, so the area is negative. So if we just go to 4, well, the base is 2, and the height here by similar triangles will be negative 10. So that's minus 10. That's not enough. So at 4 seconds, it will be here. It will be at 30 again. So how far do we have to go in time in order to come back to 0? I would like maybe at some point in time, at some point here, let me call this the base here, the base. It would be not 2, it would be slightly more than 2. Let me call it 2 times some factor f, 2f, right? Because by similar triangles, if this one is 2 times, let's say if I multiply the base by 3, then the height is also multiplied by 3, by that same factor. So this will be 10f. And I'd like to know what that f is. in order to find the, to make this thing minus 40, all right? 40. Magnitude will be 40, but I know it's turning around, so it's negative. So I have half the base will be 2f, that factor here, times the height, which is 10f, half of, and I would like that to be equal to 40, So I want, again, if I just make this one 2 and this one will be minus 10 by similar triangles, this and this are equal in area. I want it to be larger. How much larger? I don't know, maybe it's twice, 3 times, 2.5 times. So I will have to multiply the base by a certain factor, so the height is also multiplied by a certain factor, by similar triangles. So here I have f times f is f squared, and the 10 cancels from both sides. So f squared is 4, so f will equal to 2. F will equal to 2. What does that mean? It means I want this to be 2 times f, so that's 4, since f is 2, so that's 4. So if this is 4, so I have to add 4, so from 2, and how much do 2 plus 4 will be 6, so it will be 6, so it will be at 6. At 6 seconds it will turn around and become 0. So at 6 seconds it will come back to the origin. 6 seconds it will come back to the origin. I would like to redo this same problem using calculus though. Maybe you don't remember geometry or whatever, so let's use calculus. I will redraw that graph here. Here is the velocity versus time. So here is 2, 4, 6, 2, 4, 6. Here's the velocity. It started at 10, 10, and then it went like this. Right? Went like that. So first, I have to find the velocity as a function of time. So what's the velocity as a function of time? Well, you have to find the equation of this line, right? Velocity depends on time. So first, I mean, to find an equation of a line, y equal to mx plus b. So I need to find the slope and the y-intercept. The y-intercept is 10, right? So I know that y is equal to mx plus b. The x here is what's plotted on the x-axis, so that's the time. This is the slope. The b is the y-intercept, which is the 10. So I know b is 10, and then the y is the velocity here. That's the velocity part. So what's the slope of this curve here? What's the slope? Well, it's the rise over the run. So it went from 10 to 0, so the change in height is, that's 10, and then this is 2. So it'll be 10 over 2, that's 5, but it's negative because it's decreasing, so it's really negative 10 over 2. So that's negative 5, so it's negative 5. So the velocity as a function of time, you can write it as, well, it's that. It's v is equal to minus 5t plus 10. Okay, 5t plus 10. So now I'm going to use this to find the position versus time. So I know that. Let's do it again. So I know that dx dt is equal to v. So dx dt, and you integrate it. In this case, t initial is 0 to some t final. I'll just call it t, right, to some t final. And then equals the integral from 0 to some t final t of the velocity as a function of time, which is minus 5t plus 10, right? V of t, you integrate v of t. Let me write it. V of t dt equals 0 to t. V of t is minus 5t plus 10 dt, like so. Again, you take a derivative and then integrate. That just undoes when you take derivative, they just take derivative and then do the antiderivative. It just will undo what the derivative did. And so you get x between 0 and t. So here you have, okay, and then on the right-hand side you have to integrate this. What's the integral of t? Well, it's t squared over 2. So you have minus 5. So it'll be minus 5 t squared over 2 plus the integral of 10 would be 10t. 10t. Evaluated between 0 and t. And you can double check this by taking the derivative. If you take the derivative, the 2 comes down and cancels this, and you get minus 5t. And the derivative of 10t is 10, so you get back your velocity when you take the derivative. You evaluate the position at time t, that's x of t, minus the position at time 0, equals. When you plug in t here, you just get this same thing, and then you subtract, you plug in 0 and subtract it. So you get this, minus 5 over 2 t squared plus 10t minus what? Oh, minus the same thing, but you plug in 0. If you plug in 0, you get 0. So it's just 0 here. What's the position at time t equal to 0? The position at time t equal to 0 was, we were told, it was 30. It was 30 meters. So, x of t minus x at 0, that's 30 meters, is equal to minus 5 over 2 t squared plus 10t. Move the 30 to the other side, and you get x of t will be minus 5 over 2 t squared plus 10t. Move the 30 to the other side, it becomes positive 30. So that is the position versus time. So let me draw it on the whiteboard here. I'll just rewrite it on the whiteboard. It's you get v of t. V of t we said minus 5t plus 10 is minus 5t plus 10, and x as a function of time is minus 5 halves t squared plus 10t plus 30, I believe so. Plus 30. Yeah, that's correct. Let's just double check for a sanity check. Remember how the velocity looked like this. This is time, this is v. It started at 10, 2, 4, 6, 2, 4, 6, and it went like this. At t equal to 0, the velocity should be 10, t equal to 0. Let's plug in 0 for t. Yep, the velocity is 10. At t equal to 2, the velocity should be 0. Minus 5 times 2 is minus 10, plus 10 is 0. So the velocity at 2 is 0. That's good. The position at time t equal to 0, we know it's 30. So if we plug in t equal to 0 here, this vanishes, and you just have 30. So that looks good. Everything checks out. And if you take the derivative of position versus time, you get the velocity. Just take the derivative of this. When you integrate, there is that arbitrary constant that gets added, and you can determine the arbitrary constant using the initial condition. In this case, we were told that at t equal to 0, the position was 30. Okay? So now, for example, we were asked, at what time is the position equal to 0? Right? Earlier, I used this method, and I said at t equal to 6, the position will be 0 again. Here, I don't have to deal with that. If I want to ask when is the position equal to 0, I'll put 0 on the left side and solve for t. So let's do that. So for example, if the position is 0, so I have minus 5 halves t squared plus 10t plus 30. Let's multiply both sides by 2. So I get 2 times 0 is still 0. I get minus 5t squared plus 20t plus 60. And let's divide both sides by negative 5. So 0 over negative 5 is still 0. And this becomes t squared. If you divide by negative 5 here, you get minus 4t. Divide by negative 5 here, you get minus 12. And so you have, let me move the 0 to the other side, equal to 0. And we can solve this by just factoring. 0. I want two numbers whose product is minus 12. And when you add them, you get 4. You get minus 4. That's 6 and 2. And t times t is t squared. I put a minus and a minus. Minus 6 times minus 2 is positive 12. So I want the larger number to be negative and this number to be positive. So the solution to this is t equal to 6 and t equal to minus 2. Since we're interested in the time interval 0 and on, this will be the correct solution. It's the correct solution for this. Okay. That was the same thing, but one way we used geometry, the other one we used some calculus. Okay, let me see here. Okay, so now, how about acceleration? Let me just mention that because, and we will deal with it in more detail in the next video. Acceleration. First of all, there is the average acceleration. It will be just how we defined when the position changes over time, you get a velocity. If the velocity changes over time, you get an acceleration. It's the change in velocity over the change in time. The instantaneous acceleration will be the limit as delta t goes to 0 of delta v over delta t, and so it is equal to dv dt. And since v itself, so you get d dt, since v itself is the derivative of position with respect to time, so it's dx dt, so the acceleration will be the derivative of the derivative, which is known as the second derivative. So it's, t here. So it's d second derivative dt squared. Okay, that's the acceleration versus time. And I think I have about 8 minutes, so I'm going to, I usually stop at around 30 minutes. That's how much my recording device goes. So I'm going to do the following. So just to show you this, it doesn't hurt to do it once and then do it twice. Motion at constant acceleration. If the acceleration is constant, what is the position versus time? What's the velocity versus time? So let me do that in the next board. I will clean the board and then do that. So let's do that here. It's a good calculus exercise. Motion at constant acceleration. Right? The acceleration is simply a constant. The acceleration is constant. It doesn't change over time. It's constant. Why are we interested in this? Because very often the acceleration is constant. And the most common one in everyday life, it's the acceleration due to gravity. It's minus 9.8 meters per second. Meters per second downward. Oh, I failed to mention. The units for acceleration would be meters per second squared. Because the velocity is meters per second, and you're dividing by seconds again, so it gets meters per second squared. So if the acceleration is constant, it means that the acceleration is dv dt, that's equal to the acceleration, and it's constant. So I'm going to integrate both sides with respect to time. So let me write it this way. Is the acceleration. So I have both sides dt here, dt, and I integrate. I integrate from some t initial from 0 to t final, from 0 to t final. Again, here you have a derivative and then you integrate, you get the velocity back again, but you evaluate your velocity between t equal to 0, this is v of t, between t equal to 0 to t. And this is, now the acceleration is a constant, so it comes out from the integral, and the integral of dt is t, so it's at, evaluated between 0 and t. And so this becomes the velocity at time t minus the velocity at t equal to 0. And this will be the acceleration at time t minus the at evaluated at t minus at evaluated at t evaluated at 0, that's 0. So you just get this. So this becomes the velocity. I'll drop, this is just v, and then v at 0, just call it v initial, equals to at, and so the velocity as a function of time is v initial plus the acceleration times time. So that's one equation. I'm going to box. And then the next one will be position versus time. So let me do it here. Position versus time. Position versus time will be, we know that dx dt is equal to v. So dx dt is v dt. But if the velocity, if the motion is at constant acceleration, the velocity is equal to v initial, that's a constant, the initial velocity. Maybe that thing had 5 meters per second. It was moving at 5 meters per second. So that's a constant. The only thing that's changing is the time. The acceleration is constant, because that's the motion we're considering. So integrate both sides from t equal to 0 to t final. 0 to t final. And so I have the integral from 0 to t dt. But what's the velocity? The velocity is v initial plus at. V initial plus the acceleration times the time. Again, derivative integral, it just n does. So you get x of t evaluated between 0 and t. And then I want to integrate this. V initial is a constant, so when you integrate it, you just get v initial times t plus the acceleration times t. When you integrate it, becomes, you integrate t, it's t squared over 2, so it is 1/2 a times t squared. And you can double check by just taking the derivative. When you take derivative, 2 comes down, cancels the half, and you just get 80. You get back what you have started with. And you evaluate this between 0 and t. So this is x at time t minus x at 0 is equal to what? This is v initial t, when you plug in t, plus 1/2 of the acceleration times t squared, and then minus the same expression, but you plug in t equal to 0. If you plug in 0 here, 0 times v initial, you get 0, and you get 0 here, so that's just minus 0, so I will not write it down. X at time t, we just call it x, and x at t equal to 0, we just call it x initial, and so you get v initial t plus 1/2 a t squared, and so x will equal to x initial plus v initial times t plus 1/2 of the acceleration times the time squared. That's the second equation. Okay, that's the second equation. And this is really the equation that you need, because now if you take the derivative of this with respect to time, derivative of x with respect to t is v of t. So let's take the derivative of this. You take derivative of x initial, that's a constant, so that's 0. V initial t, if you take the derivative, you just get v initial. That's that. Take derivative of this, the 2 comes down, cancels the 1/2, and you get at, you get this. So that's the x, v of t. And then if you take derivative of this again, you get just a, because derivative of v initial with respect to t is 0, it's a constant. Derivative of at with respect to t is a, so you just get a, you get that. And then there is a third equation that I will show you later. Basically, if you eliminate t here, you solve for t and plug it, you will get the following. You will get the third equation is v squared minus v initial squared equals to 2a x final minus x initial. That's the third equation. That doesn't involve t. I'll come back to this next time.